Cool. So hi, everybody. I'm Monica Beckwith. I am a JVM Performance Engineer. I've spent most of my life with HotSpot OpenJDK. Before it was OpenJDK, so it was just called Sun HotSpot JVM. I started with simple performance engineering, like in the generated code, JIT instructions and everything. Moved on to garbage collectors, and then eventually so on and so forth. And now it's like the holistic JVM performance. But the passion for working with the garbage collector and trying to see avenues for improvement stayed with me. And because of that, I want to talk about ZGC, which is the newest low latency collector in OpenJDK HotSpot. See if it's working. There you go. So the way I want to talk about ZGC is kind of introduce how we build a garbage collector. What are the considerations in designing a garbage collector, and then eventually make an introduction to ZGC by the design choices that we have made with our garbage collector. And then I'll do a comparison with G1GC at the end and trying to show how ZGC's adaptiveness kind of makes it more conducive to providing lower latency. Okay. So let's start with the basic principles. When thinking about a garbage collector, there are some basic things that I wanted to highlight before we go into the deeper dive. When you look at HotSpot, the VM, the garbage collectors each serve a purpose, so to speak. So as we started, we were really considered towards footprint. So that's why we had the serial collector. And then we said, oh, okay, footprint is great, but how about throughput? Because we had more cores and we could actually many GC threads could be employed. So then we can get better throughput. So then we got the parallel collector, and then we were like, oh, throughput is great, but how about better latency as well? And scaling heaps, larger heaps, because memory, you were getting into terabytes of heap space. So that's when G1GC was introduced, and so on, and then lower latency collectors since then. So the other part of it is the whole concept of generational collector, where you say most objects die young. So when I'm allocating these objects, chances are they're going to die sooner than later. So how about aging them in one generation and then moving them to the old generation after they pass a threshold of age? So that is basically all OpenJDK collectors before ZGC and Shenandoah, they're all generational. So it started with the serial garbage collector, and then the throughput one, which is parallel GC, then G1. These are all generational. And if you're keeping track of the lower latency collectors, then you'll see that most of them are going the route of generational as well, because that helps with throughput mostly. And if all the Java applications kind of follow the same, most objects die young because you're building a cache, for example, at the very beginning, and then you're doing some transactions. So you will have many of the objects that will be short-lived. So that kind of helps with the generational concept. The second thing that I already covered is, like, as you have more cores helping out, having multiple GC threads working in parallel and doing their own work units kind of helps complete the process faster. So whatever the unit of work for GC is, that can be divided into multiple threads, and they can each do their own unit, the subunit of work, and then eventually you can come back together and you're done. So I may talk about it a little bit more later, but for now, with this simplistic approach, let's design a garbage collector. So I talked about the generational concept. I briefly mentioned about the kind of like the generation where you age the objects in OpenJDK HotSpot, it's called the young generation. And then the generation where you move the objects after they have passed the aging threshold, which is the old generation. Now, to be able to have these generations, there's this whole process of card marking and kind of trying to remember incoming pointers. And in G1, for example, there's this whole remembered set. So basically, there are these maintenance barriers. So basically, you don't, as you're moving objects, you want to keep track of what has changed or whatever. So mostly you have these kind of maintenance barriers, and that's kind of an overhead. So that's why I've shown it here in gray, sorry. The other part, which I mentioned about the parallel work, like you have more GC threads that you can employ to do the same GC work that could have been done by a single thread. That kind of helps. So if it's a GC that pauses, like it's called the stop the world collectors, then the parallel work and the stop the world period will get reduced. So the entire GC work will be completed faster. Okay. So that's why basically the parallel work is dependent on the stop the world threads, like the work that's done by the stop the world threads. And sometimes if latency is a concern, you can also divide the parallel work into concurrent threads, which are working with the application. So these are just two directions of GC that can happen just to make sure that the work done happens faster. Okay. And anytime I talk about concurrency, or anytime I talk about updating an object, there's always this overhead of maintenance, because you don't want to have an imprecise GC, right? We want to make sure the GC is not adding any corrupted data, and that the GC is not messing up my live objects. Those are the two things that we want to be sure of. So we add these maintenance barriers there. So these are overheads. So the more concurrent you go, or the generational concept with respect to regions, which I have not mentioned yet, but that they all will need some maintenance barriers. So with this basic GC, if I only want to maximize throughput and not care about my latencies, then my goal are twofold. So to optimize throughput, I want to make sure I'm employing a lot of threads, and I'm not taking away resources from my application, right? So if I could, and the GC work basically is marking, making sure that we identify the live objects, and then compacting, which is moving the live objects into an old gen space or a two space where we can have the live objects next to each other. The concept of having live objects right next to each other is called compaction. So if we don't do compaction, and if you think of your heap space where live objects are scattered and there are holes of dead objects, then it basically could look like Swiss cheese, like if you had to visualize it. And those holes are called, give rise to fragmentation. So now from a GC perspective, to know what objects are live and what are dead, it's very difficult, and it gives rise to more overhead, okay? So the goal of a throughput collector is to minimize those overheads. So we want to make sure that we are reducing fragmentation and we are not taking any resources away from our application. So the way we make sure that the resources are not taken away from the application is to avoid any concurrent work. The moment we work with the application, guess what? There are CPU cycles that go into the GC concurrent work. There is the memory barriers and other things that we are adding to it. And then there is also some maintenance stuff that I mentioned, right? So that is also the work that we are doing beyond our application work. So we avoid that. So going back to the design, this is where we were last. So if I wanted to change this to a throughput maximizer, I would take away the concurrent threads. Okay, and that would be it, because we got rid of that. We have parallel threads and we are doing compaction. So we're good to go. Now, as soon as I mentioned compaction, I think everybody is thinking about the long pauses, right? So, and that's what people will say. Oh, but there are long pauses. And why? Because we're doing a full compaction, right? So yes, a full compacting collector can get unpredictable, right? And many a times you'll find these very long pauses that you cannot deal with because they blow out your system level objectives, right? And then the other problem is, how would your GC scale with different promotion rates? So remember I mentioned about the generational collector, and after it passes the aging threshold, it promotes these objects into the old generation. But depending on how my allocation rates are and depending on these ages, my promotion rates can vary. And I want to make sure that the GC can adapt to that, can scale to these promotion rates. But a full compacting collector is not able to do that because it doesn't have that precise hold over what spaces you can promote. So in order to be able to scale well, we have to let the GC have some predictability. And that's the whole concept of G1. It's able to predict how many regions it would need to be able to maintain and keep up with the promotion rates, okay? So that means that we would have to add regionalized heap, which means that your granularity of work can be reduced to one region, right? And then the other thing is, like, don't go for full compacting collection. Go for partial compactions, which is also known as incremental compaction. So just add a few regions, don't use all of the old generation space for compaction. There is also the concept of concurrent marking, which was also introduced with CMS, the mostly concurrent mark sweep collector. And that concept is also now in G1 GC. So, so now let's look at this latency sensitive collector. I mentioned the generational concept is still there, right? And then the parallel work, I mentioned two things. I mentioned the partial compaction, right? And the regionalized heap, which, works kind of in conjunction with the parallel work, okay? There's also the concept of concurrent marking, and kind of helps with getting the work done in background because we are latency sensitive. We do care about throughput, but not so much. We're trying to meet these pause time, this kind of predictability of the pause times, okay? And of course, I mentioned about the maintenance barriers, all right. So now we're predictable, but we have these tail latencies. So you'll see that, oh, most of my pauses, and you will hear this many times, most of my pauses are okay, but there are these like 5 pauses that are not acceptable. So those make up the tail latency. So everything is good except for these top 5 or whatever. So basically what people would ask you, that's how the other GCs came about. So we need a predictable, a scalable, and a low latency collector, right? So you want to make sure that the partial compactions are great, right? Because they kind of reduce they make it very fine-tuned. They make the GC work with this fine-tuned heap, right? But what if we could make it concurrent? Basically, you don't have this one stop the world pause per incremental compaction, but you can do this copying work without the pause, outside the pause, okay? And the second thing is that if I want a predictable low latency collector, then I need to set time budgets on whatever stop the world phases. So basically, I don't want my stop the world phases to cross 1 milliseconds. So that's a time budget that I put on my collector. And then guess what? If I see that, oh, based on my prediction, if I can tell that this stop the world phase is going to take more than 1 milliseconds, then I do not do that in the stop the world. I just distribute it to the concurrent. So do some work in the concurrent phase and then go back to another stop the world. So the same 2 milliseconds pause can be actually divided into 1 millisecond pause with some concurrent activity in between. So these kind of things. So basically we're saying that we can have more pauses, but more distributed pauses. So, I mean, that's what I explained here. So you just do this basically back and forth and do incremental work in these budgeted stop the world pauses. Worst case, right? I am doing this back and forth, but I cannot keep up with the mutation of my application, basically the changes that are happening to the object graph. So at that time, if everything else fails, I want to be able to recruit the application threads. I say, hey, application threads, please help out. I'm unable to keep up with the work that you're doing. So I need you to back off for some time and help out with my GC work. And that's the worst case. So with these concepts in mind, let's design a low latency collector.
Hey, Monica, is it okay if I ask a question now?
Yes, go ahead.
So isn't this what is also called work stealing, what you refer to as self-healing?
Work stealing, so the GC threads do the work stealing amongst themselves. Okay. And that's a concept that's been there for all the parallel and threads, even for Stop the World. The work stealing concept comes from communication networking background. So you could say that, but what the self-healing is that if I am an application thread and I find out that I have a stale address, so basically I should be looking at the from space, but I'm looking at the to space, then I myself have this job to make sure that the object is clean. So it's called the dirty area. So I clean it up myself. So that's called self. I'm hurt and I'm healing myself now. So I'm putting my own Band-Aid on myself. So it's basically helping the GC out because it has no choice. It cannot touch the work in progress space. It has to go out to the other space, right? So that's why it's called self-healing.
Thank you.
Cool. So let's talk about the low latency collector. So we already know the generational concept, the regionalized heap concept, and the parallel work. So quickly, let's populate the generational. And then let's look at the parallel work. So I mentioned about the partial and incremental compaction. But because I am really sensitive to the stop the world pauses, I am going to make these partial incremental compaction concurrent. So now I not only have my concurrent marking, but I also have my concurrent compaction. And then I mentioned the self-healing nature. And so I'm going to add that here. And of course, because of the self-healing nature, remember, you cannot touch certain spaces, and you can touch the other spaces, the good area and the bad area. So you can go to the good area, and those need all maintenance barriers. So this is where ZGC is headed. I did mention that the generational ZGC is yet, it's a work in progress. So for now, if you try ZGC out, you won't get this part, and everything else is in ZGC today. Okay. So now I hope it wasn't that fast. And if it is, I can take a pause here, and if there are any questions, let me know.
So when we do the partial incremental concurrent marking, what if objects are being moved by something else, some other process at that very moment? Does that cause latency and therefore self-healing, or how does that part work? So wouldn't partial depend on self-healing?
So marking and compaction are two different things. So compaction can only happen after marking is complete. So marking is done by the GC threads. So the self-healing concept comes with compaction, and that's when I was talking about the clean area and the dirty area, right? The good, bad.
Right.
So if the application thread finds that it is in the bad area, it's pointing to the bad area, then it will self-heal to the good area. And that means no GC thread has gone to it first. And I'll show you how ZGC, so every GC algorithm will have its own way to deal with this, so that basically there's no overwriting or unknown state, right?
Understood.
So I'll show you how it's done in ZGC, but please feel free to reach out with respect if you have questions with respect to Shenandoah, for example.
Absolutely.
It's a little bit different, yeah.
I may be jumping the gun here, but I do have a curiosity about what if there is an object that is now being sort of cleaned up, and another application thread is seeking this object. Is there like a read barrier or something that?
So yeah, so there's the two-space invariant that we'll talk about shortly, and that's definitely it's called a loaded value barrier, and yeah. Okay, so let's go into designing a ZGC collector. So the reason I wanted to introduce this whole concept of how to design a low latency collector is because that's how, when you're designing a GC, that's what we think about. We think about what are we trying to achieve here, right? So there has to be these design goals, right? So in ZGC's case, we want an adaptive, almost real-time, scalable, because we want terabytes of heap space, but predictable. So we want to be able to predict that our garbage collector will not take more than, like I said, 1 millisecond stop the world pauses. So for now, as of today, ZGC does guarantee sub-milliseconds. So sub-milliseconds is less than 1 millisecond, basically. They guarantee you that. In fact, some of the phases have this, like I think 200 microseconds threshold. Like after that, they'll go back and forth between concurrent mode and then come back again, stop the world. So they'll try to do the work in this concurrent stop the world cycle until the entire work is finished. So what does that mean to the end user? Basically, your GC pauses will not increase. Doesn't matter if your application heap size is different or is larger, if your live data set is different or larger, or if the root set size is really, really big, okay? So it doesn't matter. ZGC guarantees that it will give you sub-milliseconds pause time. And what that means with respect to end user, again, it means that a ZGC heap can span from 8 megabytes up to 16 terabytes. And it guarantees you that your sub-millisecond pause times would be the maximum pause times that you will get, which is amazing. And now there's one more point that I want to make, and before we dive into the core concepts. The major part of ZGC work is done concurrently, which means reference processing and everything else is done concurrently. These concepts were introduced with ZGC, and what that means that prior to ZGC, most of those works were done in a stop the world fashion. So with G1, if you compare ZGC with G1, for example, you will find that the same reference processing is done in stop the world pause, and with ZGC, it's moved to the concurrent phase. So all this magic is now affecting the way your application throughput works. And that's why there is a goal by ZGC to not let your application throughput fall below 15%. And I haven't, in many of my experiments, I haven't seen it fall below 10. So this is really a great progress by ZGC team. So I'm happy to report that I have not observed anything worse than 10. So we talked about the ZGC work. We also talked about the way ZGC has this like the good area and the bad area concept. So let's look at how ZGC maintains this these kind of differentiation. And the concept here that I wanted to cover is called colored pointers. So this is what I've shown here is your object address, the way each object has its address. So from 0 to 43, so basically the first 44 bits are basically what your object space. Remember I said 16 terabytes, right? So that's how much addressable space you have. And then the top ones, like the 48 to 63, are unused. Therefore, the first two first two bits are basically marked 0 and marked 1, where you know that the object is marked or not. So these two will tell you if the object is marked. And so these are the phases basically. And the next phase is remapped. Okay, so which means that the object is known not to be pointing into the relocation set. So I will talk, there may be time later in the presentation that I'll talk about relocation set. But if anybody remembers G1 GC, relocation set is the same as collection set. It's ZGC has similar phases, but the names of the phases are a tad bit different. So relocation is the concept of moving, relocating from the from space to the to space. In G1 GC, we say that what are we collecting? The concept of collection, because G1 is all about garbage collection, right? So it's the same concept from the from space to the to space, but it's the collection of live objects that are moved from the from space to the to space. So same thing, just different names, okay? Relocation set or collection set, it's the same thing. And then last is finalizable. So is the object reachable? Only through a finalizer. And this is important, but I won't dive into that right now. To this particular graph and the update to it is from Pear's presentation. And so to look at the presentation, please click on that link there. So any kind of metadata will be stored in the unused bits of the 64-bit pointer. And the whole concept of these kind of regions, like what are we doing? Are we in the marking phase, or are we in the remap phase, or are we, what stage are we? This kind of concept is addressed by ZGC in this virtual address mapping phase. So basically, you would get on x86 64, and I think also on ARM 64, you have multiple maps available of this heap space. So you have 3 different maps, and that particular concept is actually called multi-mapping. So what stage are we in the mapped or a remapped or the regular, the final stage is all in 3 different sets in virtual maps. So I hope that is clear. So you could ideally, if your architecture allows so, these bits could be tag bits, so to speak, and then your address could just have these tag bits enabled, and then there's some kind of protection or fault that you can have. But on x86 and ARM64, the simplistic design would be to just make sure that each of these tag bits are actually just in different spaces. So you don't have to worry about like at runtime calculations, because you're like, oh, I'm here, or I'm here, or I'm here. And this means mark, this means remap, or this means the clean state. So now that we understand the concept behind how we keep ZGC sane, let's talk about the phases. Okay. So to explain that, what I've done here is showing some application threads. So this entire big arrow is a bunch of application threads that are running, and it's showing over time, basically. And then there are some background threads that you can see in this greenish blue, some color combination that I chose. And what I wanted to, the reason I said background threads is because I want you to know that this is a concurrent activity, and there are sets of adaptive thresholds that will trigger ZGC and different phases of ZGC based on the occupancy and other considerations. And I'll talk more about it when I talk about performance numbers. So let's just for now consider that these background threads are doing this job of looking at various knobs, right? You have this control panel in front of you, and they're just looking at different knobs to adjust them so that they can trigger ZGC phases. So at this particular time, this time slice in pink, the background threads decided that we need to start a ZGC pause, and it's called pause mark start. Again, if you compare this with G1GC, it just means initial mark, right? So pause mark start is also initial mark. Okay, and then what happens is, because so it does stop the world, right? But after that, we do our concurrent marking, and in ZGC, we also do the remapping here. And this is the phase. There are a lot of, it's similar to how G1GC does concurrent marking as well. And if we go back to G1GC, so we have the initial mark, and then we have the concurrent mark, and then we have the remark, right? So of course, in ZGC also, we have the same thing, but it's called pause mark end. So pause mark end is remark, okay? And then there is something different. So now up until the pause mark start and pause mark end, we're talking similar to what we have in G1GC. But remember, I said that the partial compaction is achieved via the concurrent process. So because we're trying to do this concurrently, we will have this concurrent prepare for relocation phase, where we're trying to figure out our collection set, or how they call it, how ZGC calls it, relocation set, right? And then this pause relocate start is where we will say, hey, let's sync up everything, and let's make sure that our relocation sets are ready. And then we start doing the relocate in the background, while the application threads are running. So overall, these are all the phases that a ZGC cycle goes through. So from pause mark to concurrent relocate is the entire concurrent marking and relocation cycle. And then again, you'll go back your background threads, so start again and see if they need to trigger. So it'll keep on repeating itself. So this is a cycle, then another cycle, another cycle. And that's how ZGC keeps up with the application. Now let's dive into concurrent mark. The way ZGC does concurrent mark is by stripes. Okay, and so you take the entire heap, and because it's not generational yet, so we can just like take the literal entire heap, and then we can assign our GC threads like this. So for this particular application, I have n GC threads, and each of these GC threads will deal with chunks of heap. So because we have n threads, let's divide these chunks into 0 through n, right? And so on and so forth. So you see this repeating because I only have n GC threads. So we'll do 0 through n, 0 through n, 0 through n, 0 through n. And what will happen is that each of these threads will work with their own stripe. So stripe 0, so basically this, let me see if I have a pointer right here. So 0 will work through this one, this one, this one. 1 will go 1, 1, 1, n will go n, n, n. So that's the work area that each of them work in. And as they, depending on what is in that area, how many live objects are there, blah, 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 they can move on to the other one, another one. And once they're done, they come back and see if they need to help out others. So it's kind of like the concept of work stealing, but only after they're done with their own work, right? So as I mentioned, GC threads will work on their own stripe. And the reason is that if you have a large heap, like terabytes of heap, imagine having multiple threads kind of work being either overlapping or depending, dependent work. So if that was the case, then you wouldn't, it will take a long time to finish marking the entire heap. So you want to minimize the state that's shared. And the way we try to do that, if especially there's a load to a non-marked object, and it goes back to your question, Chandra, you need a load barrier. So load barrier will detect loads of non-marked object pointers.
So in this case, it would be a self-healing load barrier.
It could be if the load barrier, so it could be that it's in the queue of a GC thread already that I need to do that. So then the GC thread will take it. Or if it's not in the queue, then there may be in queuing or the healer. Yeah.
Okay, makes sense.
Monica, I do have one question over here, and this might be a bit more basic and fundamental, I guess. So in this scenario, we're saying that the number of GC threads is sort of fixed and it's going to be predetermined. Is that right? Because we're dividing it all into these strips, so that number is already predetermined. Is that right?
Yes. Okay. Always, I mean, and that's not only true for ZGC. It's true for OpenJDK HotSpot. So depending on your core count, if you don't specify any GC threads on the command line, then it's like 5/8 of your total cores available to the GC, to the application, basically. And so
that was my follow-up question, like how do you determine that number? So it's predetermined, and there is an algorithm for it. Okay.
Yes, and it's always been there since parallel GC threads were introduced.
Okay, thank you.
All right, so the last thing I wanted to talk about was the concurrent reference processing. And again, I'm bringing this, I'm calling it out here because lots of people only know reference processing to actually happen during a stop the world process, but ZGC has taken that out of the stop the world process and actually does it during concurrent marking. And very important because many times in the past, if you have, we used to do a single threaded reference processing, and then we kind of, I think JDK 9 or 10, we moved to G1 being able to do reference processing in a multi-threaded fashion. So it's really an improvement to even move it to the concurrent marking so that the stop the world process can be reduced. And the whole concept of thread local handshakes, and I won't go into detail here, but I talk about it in some of my G1 presentations. This whole concept of thread local handshakes, where you don't have to wait for a global event, global handshake event, which is where your safe points. If we talk about when we need the need for a GC, or we do a safe point, all threads have to come to a halt. And then a safe point, a global stop the world event would happen, and the GC threads would start their work. But with ZGC, they introduced the concept of thread local handshakes, where each application thread can transfer the thread stack to a GC thread so that they can do the roots, right? So they have to go through the roots and everything. It can do it very quickly, and the application thread can go back to resuming its work and doesn't have to wait for this global event to happen. So these are called thread local handshakes. Also, so it's pretty cool. It's introduced by ZGC, and if you have time to read about it, go ahead and do that, please, because I thought it was pretty cool.
And the thread local handshakes are miniature stop the words?
Mm-hmm. Stop the words for each thread. So each thread doesn't have to wait for the other thread. So if you had 100 threads, you're not waiting for a global event to happen.
Other 99 can still, yeah, the other 99 continue working. Okay.
Yeah. So with that, let's talk about barriers. So if I had to define like the whole purpose of a barrier, it's basically trying to update a bad reference to a good reference. So basically what it means is that we always want to make sure that the two-space invariant is followed or is guaranteed. And what that means is that anything and everything, like any object, when I want to access an object, it has to be in the two-space always. So if my reference is not updated, then it's my job to do it. Like I said, the application thread and self-healing. So that's the next point, right? So as long as I'm maintaining, the garbage collector is maintaining the two-space invariant, then all I have to make sure is that a bad reference needs to be updated to a good reference. And that's the mantra now. So you can have a self-healing or repairing barrier as long as the source memory, if somebody is doing the update to the source memory, right? So make sure that the bad reference is now a good reference. It doesn't matter who does it, right? So all that matters is that we impose those invariants. So anytime you have a visible loaded reference, visible means that it could be by the GC thread or by the application thread. So it could be visible to any of those. It will be marked through. So we make sure that we mark it, right? And that's it. That's the job of the collector. So either who does the mark through doesn't matter, as long as somebody guarantees that mark through happens. And that's the invariant right there. And the second one is, again, all visible loaded reference values. They always point to the two-space, right? The contents of the target. It's always to the current location, always to the good location. So those are the two guarantees that this barrier. So if you think of the barrier, it has only two jobs. So that's what I'm trying to say here. As long as it does both its job, and it will, because otherwise it's a corrupt heap. So that's the invariant that we have enforced. So ZGC has enforced this invariance. And actually, as a matter of fact, these invariants actually were first discussed by Gil Tenney in its C4 collector. So this, if you have interest in knowing more about these invariants, then please go ahead and read the C4 collector's original paper that I've linked here.
That is interesting, though. I do have a question. It's a silly question, please, and it may not be related to the page you're on. But so there is no snapshot at the beginning kind of marking process in ZGC. Is that what I'm understanding?
Yeah. So it's so here we go. Oh, okay. Yeah. So this was concurrent marking phase. So we marked the entire heap. So right. Snapshot at the beginning is important for Shenandoah and for ZGC, not ZGC, sorry, G1 GC. And right. That's because it uses the concept of finger. So anything above the finger is supposedly live, and anything below is actually determined to be live or not. So but that finger is the most important thing. But what we're doing here in concurrent marking in ZGC is that if you think of it as multiple fingers, right? So we're striping these things, and so we can work in multiple spaces. So if for example, in the same here, if this was G1 GC, you wouldn't see any of these stripes. You would just see this finger, and it's going to be per region or whatever. Like it's
so it's at a single sweep. You're going across everything in ZGC rather than go incremental regions. And okay.
Yeah. So it's a little bit different. One thing that, if I have time, is to measure the overhead. Yeah, because I think it's about time, because there are 2 GCs out there that are doing SATB, and which is snapshot at the beginning, and then this one is doing the stripes. So it'd be great to measure the overhead, especially with larger heaps and larger heaps that have that have a lot of live objects or mutations or whatever. So it'd be nice to see that.
Yeah, so I think Hazelcast JET, I know I shouldn't be talking about a vendor company, but they have actually done a performance analysis between the two. And it was quite interesting to see that ZGC seems to operate better at higher memory capacities. It was interesting to note that it's, I would have assumed with Shenandoah or even with G1 GC, with the snapshot at the beginning, you are more conservative in your collection and you can sort of quickly go through the GC process. But the mixed space collections is probably where you're going to get the hit. I think with ZGC, you don't have that concept anymore. It's all one single collection. Am I thinking about that right?
No, actually, it's still incremental compaction. By collection, I think you mean the compacting phase.
Compaction, correct.
Yeah, so it's still incremental. It's the same similar concepts. But if I had to guess, I would agree with although I haven't read what they're measuring or how they're measuring it, so I'm not going to make this blanket statement. But just based on the concurrent marking algorithms that I've seen, I would say that ZGC is probably going to be better because I know the disadvantage of SATB, like you said. But remember, I mentioned that there's a whole concept of implicit live and explicit live. So the finger pointer, anything above, is implicit live. So imagine that's the overhead that we carry forward until the compaction is done, and so on and so forth. So it's like a matter of who is doing the work and how much of the work is useful. So I would still need to see Hazelcast's the study that they did. So I'll have to get back to you, but I can probably, after I look at that, can explain why in their particular case that happened.
I don't want to hijack this conversation with those, but I did put in 3 links in there for the comparisons between ZGC and Shenandoah for anyone who's morbidly as curious as I am. I don't know why I am, but yeah, it's in there. So at the end of the session, maybe if we have time, we can go through those.
Okay.
Great, thank you.
So now this is a new concept, concurrent compaction. It's new for ZGC and of course for Shenandoah as well, because they're both concurrent compacting collectors. For concurrent compaction, we want to make sure that we, of course, have, because remember, anytime I mention concurrent whatever, we have these load barriers or any kind of maintenance barriers. Doesn't have to always be a load barrier, but so in this particular case, we have a load barrier to make sure that object pointer to detect any object pointers into the collection set. Again, this is a whole concept. The collection set, oh wow, I wrote collection set, but I meant, whatever ZGC, the terminology that ZGC uses, which is relocation set, right? So I should probably change that to relocation set, but it's the same thing. Relocation set is collection set. So this is not technically wrong. Again, the whole same concept. Anytime I'm talking about load barriers, if the application threads can help out, great, let's employ them. What is, again, when people ask about comparison, and like you had asked Chandra about the concurrent marking, there's also this concept of how does concurrent compaction differ between ZGC and Shenandoah. I think one of the advantages with respect to ZGC is this off-heap forwarding tables. So the whole concept of compaction, if you think of an object, the from space and the from address and the to address is actually in the header. So I did not do this in this presentation, but usually I talk about the object headers of the objects, and then in that you will have the from and to space. So in the first version of Shenandoah, you had that forwarding pointer or indirection pointer to
the Brook pointer. Yep.
Yes, yeah. So the indirection pointer to the actual location. So from so basically to the actual one, the correct location, right? So the good pointer. Then Shenandoah changed it to the whole utilizing the header, right? So the from header gets changed into the to header address. What is interesting with ZGC is all that the forwarding information is basically off heap. So you don't need to update the header per object or whatever. You can just look at the forwarding table off heap and say, oh, okay, that's where I have to go. Where do I have to go? I have to go there. So there's not much of a congestion point with respect to, okay, who's updating the header and how do I get the information? So from header and then to anyway. So the point I'm trying to say is that off heap forwarding tables are very fast, and the best thing is that as soon as you are done with the from space, you can immediately reclaim that, right? Otherwise, unless you know that the two spaces is available and physically assigned, right? You couldn't get rid of the from space area. So just an advantage that you get with ZGC. You get the same advantage with C4 as well. So I wanted to talk about production readiness, and I apologize, this slide deck is 3 months old at least. So it's talking about JDK 15 and 16. By the time JDK 15 was out, ZGC was production ready. So what it did to be able to be production ready is as follows. In JDK 10, they released thread local handshakes, which kind of helped with reducing. Remember, now these handshakes are individual threads, so they don't have to wait for all of the threads to come to safe point. The second one was the load barriers and the colored pointers, which were introduced in JDK 11. Concurrent reference processing was also JDK 11. Concurrent class unloading is JDK 12. And the unused memory, uncommit unused memory, which I discussed briefly earlier, JDK 13, and compressed class pointers in JDK 15. So with these kind of support that they tried, so when I say JDK 10, that means that since JDK 10, there have been it has been included in ZGC. So now it's been time tested, right? Over all these releases, it's been time tested. So with all that, ZGC team thought that it's ready to go. Now, luckily, I have a little bit of a preview of what thread local handshake is all about here. So Chandra, I was trying to explain this because I forgot that I had a slide here. So this is where your safe point is requested. And right here is what we call time to safe point. So basically all these threads take their own sweet time. And apparently this one took a long time. So unfortunately that becomes your time to safe point, where the last laziest thread comes to a halt. Only when the last thread comes to a halt is when we can start the GC work. And that's what you see right here. So, and then finally the GC is completed right there and the applications can resume work. With thread local handshakes, each of the threads, even though they take their own sweet time, but they can get with their handshakings, like whatever is needed from them. So for every GC process to happen, there's a lot of things that need to be exchanged. And I'd give an example of thread stack, for example. So let's say this guy's thread stack and this person's thread stack, and this all these things are called handshakes. As soon as the GC thread has that information, it will do its work. So remember, the same GC threads that I'm talking about, the work that needs to be done, it literally can complete right here. So even before the time to safe point here. And by the time this GC thread gets done with this work, it's right here, and the application threads which are already going on, they can still continue working right here. So the entire work that took these many seconds or microseconds to complete actually can be done just with these 4 handshakes.
So
in this particular example.
If you don't mind me interrupting, for the benefit of the audience, can you please explain the save point? That may actually help generate more questions.
Sure. So whenever GC threads want to understand and collect, so there are a lot of thresholds in a garbage collector, and sometimes these thresholds are triggered so that the heap doesn't get filled. So at any given point, to be able to gather information of the status of an thread's work, which is just called mutation. So to be able to get a hold of the mutation, the GC threads will stop the application threads, and this process is called a save point. At save points, what we're trying to do, what the GC thread is trying to do, is gather any information with respect to the root set, for example. And one of the things, for example, like I said before, is a thread stack. So each thread has its thread stack. And when we come at save point, we're trying to traverse from the root set and trying to figure out what objects are live. So what can I reclaim? Basically, the job is garbage collection, right? So what space can I collect back and give it to the applications so that they can keep on allocating more objects? But to be able to do that, we need to start from the root set always. So GC always needs the root set. And the save point helps us get to the root set without the application interfering, or at least giving us information. And then we proceed doing the concurrent work or parallel work. So for example, in parallel GC's case, we would always be in this global stop the world because there's no concept of concurrent work. So this would never happen. So I hope it provides you a little insight into why this is useful in a concurrent GC, but not really in a parallel GC. So prior to this change, G1 GC, even though it does concurrent marking, had to wait for all the threads, which was a waste of time. But now G1 GC can do this as well.
So out of curiosity, what happens if there is a dependence of an object on another object? I know we talked about the root sets, but let's assume an object in that root set graph depends on an object and let us say another relocation set. So is there another register or buffer somewhere we maintain on the connectivity and liveness checks for those?
So you're saying that your root set depends on?
No, let's assume an object in the graph depends on some other object, which is in some other relocation set, not in the relocation set I'm currently working on.
Yeah.
So where do I maintain this dependency when I'm doing a liveness check or when I'm doing when I'm marking, for example?
Yeah. So there's this concept of remembered sets, right, where we always talk about any. So even if I don't call it, I'm not going to go into the details of all these remembered sets and all those things, but think of it. Every region has some data structure that remembers any and all incoming pointers. So this whole concept of who is pointing into me is always maintained, and it's always accurate to a certain granularity. So it could be it could be one object in region A can say that I know that region B, someone in region B is pointing into me. So keep region B around, for example, right?
Got it.
So now if region B becomes it becomes a contender for collection set, for example, then I would be like, oh, hold on. I think that was important to me. So now let's go and figure out which object is important to me. So then you go into deeper granularity. So that's.
So it does traverse back the graph or multiple graphs. Okay.
Different graph, but yeah. Because marking is just making sure who is live and who's not. That's it. So yeah.
Yeah, so my apologies for all these questions. I'm trying to mind map all of this to how the G1 GC cycle looks like. And I'm trying to see if they have the same flows as the G1 GC, two hemisphere map.
Yeah, yeah, cool. No problem. Yeah, no problem at all. Yeah, it's always the same. It's even if you think about card marking, that time it was like what, 512, the size is 512 kilobytes or something. Right. And it was the same concept. It's always about incoming pointers, right? We want to make sure we're not killing off any dependencies of objects here. So yeah. So now to performance comparison. Now that we know that both G1 GC and ZGC have different considerations with respect to their design, let's try to break them. Okay, so the first thing I want to do is try to introduce fragmentation. If anybody remembers when G1 GC was new, fragmentation, even though of course it does incremental compaction, there were different ways to introduce fragmentation in G1 GC, especially through large objects and then if you remember CMS before that, CMS had different issues with fragmentation with respect to the varying object sizes. So I've tried to put this amalgamation together of just trying to break the collectors. So for this particular one, I am using an ARM system that I had access to then. And I'm using a JDK 16 EA because, like I said, this is about 3 months ago. And that time I had an EA. I'm using a benchmark called Heap Fragger. I think it's by Gil Tenney. And I'm testing, of course, both the garbage collectors. There's some information. So if you use Heap Fragger, you would need to know the heap size and the log data set. And then I've just had two options here because I'm using 200 gigs. I just want to make sure I'm using large pages, and I'm also doing always pre-touch. Just very simple. And of course, the heap size, like I mentioned. One thing you can set with Heap Fragger is the allocation rate. So I've set it to 1 gigabytes per second. And I think on the command line, you can also talk about object sizes. So I tried to make it anywhere from 128 bytes up to 32, little over 32 megabytes. And that's where I introduced the concept of large objects, right? So one of the things where G1 struggles with is with respect to when the large objects are short-lived or whatever. So then you have these kind of contiguous regions, and depending on how we can, so there's different ways to introduce fragmentation. I'm just trying to do that over here, okay? And now I want to make sure from what I observe from the graphs, I want to make sure that I am looking at, I'm actually getting or observing the characteristics that I induced. So earlier I mentioned about this whole thing, right? I'm just making sure and kind of validating it with my graphs, okay? So what I want to see is my allocation rate and promotion rate. So I mentioned that I had an allocation rate of 1 gigabytes per second, and it seems like to tally with that. So if you look at here, it's 1 gigabytes per second right there. And what I wanted to make sure is the live data set, right? And I mentioned about short-lived objects and stuff like that. So this particular thing will eventually form my live data set. And as you can see, basically a live data set is things that survive the aging threshold, and then they stay in the old generation. And that's the set where we do any of these kind of intermediate transactions. So stuff that lives long and helps with the entire work that the application needs to do. So as you can see, this entire live data set was promoted into the old generation. It kind of stayed in the old generation. And after that, you see the smaller ones right here. Those are these ones. These are the transactions, and these objects are dying young, basically. So what I'm trying to show here, that this particular application with all the contortions that it is actually following the generational hypothesis really well. Okay. So ZGC is not yet generational. So how does ZGC handle this kind of fragmentation and this workload that's suited for generational heap? So what you see here is the pause time in milliseconds. Okay, so this is a runtime right here, and this is the pause time. So you see everything is less than 0.34 or almost 0.36 milliseconds. 0.36 milliseconds. Okay, so basically you have the initial mark, the relocate start, and then the mark end right here. So all these are stop the world phases, and those are all less than 0.36 milliseconds. Now, that's great from ZGC's perspective. It could handle severe fragmentation. It could handle, it degraded gracefully, which is what you expect of a low latency collector. Do not give out the sub-millisecond promise that you had, right? If you cannot keep it. So it looks like it kept it. But what about the application, right? So this particular tool is again from Gil-Tenney, and what it shows us on the right-hand side is any of the stalls that are observed by the application. So when ZGC was trying to keep up with respect to the issues with the application itself was observing some stalls. And what we see here is the worst case latency that the application could observe was 350, less than 350 milliseconds, okay? So let's see, let me go here. So for the same time, if there was the worst case, depending on different situations as we did, there was a worst case, but that was still less than 0.55. This is the second run with the worst case of less than 0.55 milliseconds, but the application only saw 350 milliseconds. So remember I said that I changed the object size and everything, but for both of them, we saw that the application did not see any stalls more than 350 milliseconds. So is that great? I don't know yet, because remember, ZGC is only worried about keeping its own pause time goals under control, right? At less than 1 millisecond. So are we inducing an issue at the application's end? I don't know yet. So let's compare how G1GC handled it. So like I said, ZGC was, how much did I say? It was like less than 350 milliseconds, right? Look at G1GC. The worst case for G1GC is 10 seconds. 10 seconds. So the application saw 10 seconds pause, right? And ZGC's, while for ZGC, the application only saw 350 milliseconds, less than 350 milliseconds stall. So yes, G1GC is not designed to be a latency sensitive garbage collector, although it tries to meet these goals. But I had this heavily contrived application where I was just trying to get the worst GC behavior possible. But what I'm showing here is ZGC was able to meet expectations and even beat expectations when you're comparing with G1. So that's one. Then there's another thing that I tried to play with, which was object sizes and higher allocation rate. I'm going to quickly go through this because we're almost close to the end of this thing. But again, all this information is here. For this particular one, I'm using a benchmark called HyperAllocate, and it's by AWS team. AWS is Java team. And I'm using allocation rates at 1 gigs per second and 4 gigs per second. Again, object size is minimum 128 to maximum, such that we can have large object sizes available to us.
Out of curiosity, are they now just called large objects? Is it no longer called humongous objects?
Yeah, humongous objects. I think the reason I'm using large objects is because ZGC calls it large objects or something like that. I just don't remember. So it's so interesting to me that each garbage collector comes up with its own terminology, but the concept is the same. So I'm thoroughly confused, but but what I mean to say is that the concept remains between the humongous objects and large objects, but I haven't heard CGC use that term. So
got it. But they use the same mathematics to calculate Z page sizes as they do region sizes with humongous.
Yeah, I think so. I would have to go back and see if anything changed, but from what I remember last, it's the same similar concepts. But they also have the concept, the sizes, the region sizes are adaptive, so they can have a mix of region sizes. So just to they cater the region sizes to the object sizes, which is the opposite of what G1 does.
Got it.
Yeah, so it'll be good if you can just go through the source, and maybe I should do that and put it up here. So maybe I'll do that later. I'll add a couple of slides on the way ZGC differs and the way it handles region sizes based on object sizes. It's a little bit different, and I didn't want to go into the detail here, but I just wanted to show that I'm trying different object sizes, and because ZGC is more adaptive to the object size, it's able to adjust better than G1, basically. So remember I talked about this particular benchmark, and I'm changing these kind of allocation rates. So what I want to show here is that when the marking, so initial mark start again is initial mark, right? So at initial mark, what we were seeing was that the capacity, the black line on top, that shows you the capacity. The capacity was up until 200 megabytes per second in the occupancy, and megabytes, sorry, 200 megabytes. And you see those triangles, that's the used space, right? And I think there's an error here. I think this is a tool that we use internally, and I think it's showing a little bit of error here. It should be gigabytes, of course, because remember my heap was gigabytes. So yeah, this tool just needs to work better with ZGC. So yeah, so LDS here is 100, and the heap size is 200. So what we're showing here is that before initial mark started, we were trying to spread out to the live and the dead objects or whatever are spreading out to the entire heap. But at the end of location end here, what we see is that our LDS is 100, basically, is what I'm trying to say. So this is, again, validation of what I wanted to happen to make sure that it is in fact happening. So short-lived objects, yes, because remember our LDS came down after marking was done, after relocation was done, and we see these objects here. So that's pretty cool. So that's a validation that 100 gigabytes is our LDS. Now, before I go and show the results, and this is kind of helps with the adaptiveness of ZGC, there are different phases that ZGC. So when I mentioned ZGC's background threads. So this is what those background threads help with. It kind of lets us know if we need a proactive GC or not. If they also help us calculate if we're going to have an allocation stall, or if the allocation rate is too high, or there's a high utilization of the heap, like you are a really big heap utilization and we just cannot, the garbage collector cannot keep up, or just to warm up the gears, or like, turn the gears to get ZGC started. So these are the different phases that ZGC can go through. Sometimes if there's no collection whatsoever, then you just collect based on a timer, right? So that's the timer thing. So that's why I mentioned those background threads, because there's always these things happening in background, and that's the adaptiveness, that's the proactiveness of ZGC that you don't find in other collectors. So with that in mind, I want to show how the allocation rate and allocation stalls with that application that I had shown back there, how that kind of happens, how ZGC goes to that phase. And let's just define it very quickly. Allocation rate is if your application has higher allocation rate and eventually could run out of heap space. That's when ZGC triggers the allocation rate cycle. And the second one is allocation stall. Basically, your mutators are blocked and you say back off. ZGC says back off, you cannot allocate anymore, or else we're going to have a, we will run out of space. Okay, so those two I want to show right here. So remember, my application has very high allocation rates and short-lived objects. So even then, and this is really, really contrived with 100 gigabytes of LTS, I see allocation duration. Basically, I stop the work duration of 2.1 milliseconds. So this is JDK 16 early access. I found that, yes, I was able to sort of go past the 1 milliseconds past time goal right here, with the worst case showing to be at 2.1 milliseconds. But how did that translate? How did that translate to the application? Okay. So in the application, remember I said allocation stalled because ZGC told the application back off, I cannot keep up, right? Because I had kind of contrived the application so badly. So here we see that the application still did not see that many, even though it was stalled for a while, it still, the worst case was less than 130 milliseconds. So that's what is showing in both the graphs here, basically showing less than 130 milliseconds right there. And how did G1 GC do? So G1 GC, this is the worst case right here. The worst case for G1 GC was 1.25 seconds, 1.25 seconds. So again, your application, because of all the stalls and everything, sorry, let me go back, was less than 130 milliseconds, but G1 GC, with all the pause times and stalls, could actually was worse with 1.25 seconds. So that's it. That's all I got here. Again, I just wanted to, again, compare quickly with, kind of put those two side by side. So one is G1 GC, 1.25 seconds, and the other one is ZGC with less than 130 milliseconds. So with that, when I talk about different tools and different presentations that I kind of tapped into to make this particular presentation here, the graphs that I showed about application stalls are from histogram log analyzer. JHiccup is another tool that talks about how to get your how the stalls in application. And of course, Sensum is the internal tool that I was talking about. I also have some JFree charts and GC Histo plots that I've shown here. And that is it. Thank you very much.